Hello, I am Jacob Barnhill, and
Daryl Jones.
this is our Risc-V single cycle CPU. Be going through each individual part, explaining how it works, and then demonstrating it working.
Alrighty, starting from left to right, let's go with the program counter. Let's explain what it does.
All right. So this program counter is pretty simple. It keeps track of a number, and every clock cycle it updates the number to +4, unless specified otherwise by a branch or a jump. But it will loop through 4, adding 4 each cycle.
All right.
Pretty simple, I'd say.
Next, connect it. Let's explain the instruction memory.
Well, not yet. I would say let's go to this adder right here, because this
All
is
right,
the
let's go to that.
instruction loop. So it's right out of the program counter. We go to the instruction memory, which stores our assembly. It's what we write down and tell the CPU what to do. And then up here, the line goes to our adder for our program counter. And all this does is add 4 to the current number. And then based on whether we're branching or not, this will go straight through and back into their program counter. So it just makes a small loop.
Let's move on to the next part,
Instruction
which is
memory.
the instruction memory.
Instruction memory is pretty simple. I did not use the full 20 or the full 32 addressable limit, as there's no need for this project to demonstrate it working. Only one ROM is necessary, which uses 24 pins instead of full 32. So that's why I did not use all 32. And I have them spaced out 4 bits apart by not using the first 2 bits.
Can you explain what's going to happen from the information that comes from the adder as it gets put into the ROM?
In here,
Mm-hmm.
okay, so this is coming from our program counter. And what this does is it selects a number. So I can't really, let's see, can't really show this as high or not, but depending on what address is selected in the program counter is what number is chosen in this little memory. And whatever number is chosen in this memory is the instruction that is sent to the rest of the CPU. Anything else?
Nope.
All
Now
right.
it takes the numbers from the instruction, and now we need to figure out where that goes.
Yep. All right. So the instruction kind of goes a little bit everywhere.
Right. Uh let's start with signal control.
Signal control. Okay. So this is our signal control. What we take from here, we take our instruction and we take the first 7 bits, which is classified as our opcode, and that determines what type of instruction we're doing. And if I open up the Risc-V reference right here, opcode is the first 7 bits of any instruction, and that is a determinant of what type of instruction we're about to do. Depending on the type of instruction, we have to send out different signals for what to do, such as an R type. We need to write to a register. We don't use an immediate number, so we're using RS1 and RS2 in our registers. We're not writing to memory. We're not branching. We're not sending anything from memory. We're not jumping. So these are all low. And that is done with this little controller right here. So if you see, if R type is high, if we know we have an R type, then we're only going to be doing register write right here.
Right.
Any more questions or?
Just to clarify, the numbers that come from the instruction type are only going to go to its designated uh, control type, right? So like if you get 0 or 1, you'll only get R or I.
Yeah, there's only one type is possible at a time.
All
And
right.
that's um made sure of with these little bits right here. So all of these have to be high, but these values are knotted, so they have to be 0. Like if it's a J type, then it would be 1, 1, 1, 1, 0, 1, 1. And that's only possible at one like only one of these is on at a single time. And I find these values for what type based on the reference card right here. See here, all of these right here are R types, and they all have the same opcode. Right here,
Gotcha.
I types, they all have the same opcode. The J type down here, same one opcode. B type, S type, these are I types.
Gotcha. Alrighty. I think that makes sense.
And these little values get sent out a little bit everywhere. They go a lot of places. They control a bunch of these little muxes right here. Like the jump signal controls this mux. Register write controls whether we're writing to the register. ALU SRC determines whether we're using RS2 or our immediate and a value from immediate. Memory read write is determining whether we're writing or reading from memory. Branch determines whether we're going to be doing branch. And memory send is determining where we're sending something from this little memory selector right here.
Okay.
All right, next.
Let's talk about the instruction parser, because we're going to need to go into it for the register bit.
Yep, instruction parser. What this does, I think it's pretty simple. I split everything up. So here I have opcode. This isn't really needed here, so I don't send it anywhere. It has no output. Here is the next few bits. So this is RD. And if we look at our reference, RD is bit 11 to 7. If we look here, 7 to 11, that's our RD. This is the address for the writing register, so what register we're writing to. And that is always in the same spot. And then we have this right here. Get the selector, which is function 3. These are 3 bits, 12 to 14. And these bits are always 12 to 14, as shown on the reference. And then next is RS1, which is bit 19 to 15. That is the register address for register 1. And then register 2. And then function 7. Func 7, which is the last 7 bits. Any more questions or?
Is there, can you explain why there are, what is it, 6 inputs going to function 7?
There's 7. 0 through 6.
Okay.
0 is one of the 7.
Okay, gotcha.
Yep.
All right, I think that's good.
All right. After we, what's next?
Let's go into the immediate generator.
Immediate generator. This one's chunky. Chunky. So, immediate generator. Pretty much, this takes our inputs. It takes the opcode, determines what type we have, and then based on what type we have, we take our values depending on our construction format here. So this is, just for an example, this is IMM 11.0. So bit 0 to 11, which is 12 whole bits, right from here to here would be 12 bits, is our immediate value. So it just represents a number. And if you see right here, this is an I type section. And we're taking bit, I think that's bit 20 to 31, which would be 12 bits. Bit 20 to 31, 12 bits. And we're extending that to 32 and sending that through as our value if we have an I type.
Okay.
Cool.
So how does that relate to the rest of the types? Is it the same?
Well, depending on the type, not every type has the same immediate number. So an S type, for example, has bits 5 to 11 right here and 0 to 4 right here. Because an S type doesn't have we're not writing anything to our registers for an S type. So that value
Right.
is used for the immediate instead. If we go
Okay.
to S type here, we get our value from this right here. And I mean, it's not as easy to see, but it is split up that way.
Gotcha. What about the sign extended black box squares?
Which one? This one?
Any of them, just
Any of them?
explaining like, yeah,
Okay. So
any
these need to
one.
be sign extended to 32 bits because we have a 32-bit CPU and we run
Mm-hmm.
the process on 32 bits. So all of our values for our immediates are sign extended to 32 bits. And then this right here is sign extended to 32 bits if it's true. So say if we for sure it's an I type based on our opcode, then this would be high. This would be a 1. And then its sign extends to 32 bits. So this would be all ones, right?
Mm-hmm.
And because this is all ones, and say we have our value here, and we go through an and, then this would just be our value.
Gotcha.
So this is
Okay.
enabling our value to get sent through this giant OR. So only one of
Right.
these would be sent through at a time because it can only be one type at a time.
Gotcha. That makes sense.
Cool.
Alrighty. We're good with this one.
All right. What's next?
All right. Let's get into the 32-bit register.
32-bit register. I've covered this in a previous video, I believe, but I'll cover it again. This is the 32-bit register. I'll start with our inputs. Oops. We have an input of RS1 address, RS2 address, RD data, register write, register address, clock, and reset. Clock only updates the value of a register when the clock ticks. So when it's high, a value is able to be updated. When it's low, nothing can change. Reset resets all values to 0. Doesn't matter what state it's in, whether clock cycles or not. RS1 address is the address for the first register, depending on our outputs here. So the only thing this controls is what output we're looking at for RS1 data, our output, and RS2 address is determining what output we're looking for RS2 data. And all this does for RS2 and RS1 data is looks at the value stored in each register. Great.
Gotcha.
RD data in, this is the value that we're trying to store into a register. So we're inputting a value into our system, and that is what we put into RD data in. RD address is what address we're writing our data to. This is 5 bits for 32 values, 32 registers. And then register write en is register write enable. So this is only high if we're even writing anything to begin with. So if we're not writing anything, then this is off. If we're going to write something, then this is high. And this sends the high value to the select address of the register.
Mm.
Any more questions?
All right. Nope. I think a little brief explanation was nice. Can we come out of this?
Yep.
Since we've already covered it, I think it's just better to explain how that data from the instruction parser as well as the sign control will come into the register a
Yep.
bit, and then how it'll be influenced also with the ALU control decoder. So we can explain what the ALU itself does.
Well, I'm not going to explain the ALU because I have a detailed video on that if you want to go watch that
Right.
one. But I will explain the register write en is coming from our signal control, as I've explained earlier. Depending on what opcode we have, depends whether we're actually writing something to our register. So, for example, if we have an RD at all, we're usually writing something to our register. So if there's an RD, then register write EN would be high.
Gotcha. And then for the ALU control decoder, just to show it.
ALU controlled decoder. This is complicated, but I'll get into it. So this is a whole jumbled mess of complications. And let me start by showing the reference card. So in the Risc-V CPU, these are all of the operational instructions we're allowed to do. Or not what we're allowed to do, but what we should get ready for. And these are determined by a function 3 and a function 7. So depending on what function 3 and function 7 are, is depending what instruction we're doing in our ALU. Now, most of it is derived from what function 3 is. Right? See this? The only way function 7 is used is to determine the switch between addition and subtraction, and then shifting right logical and shifting right arithmetic. So if we have a function 7 at all, then it goes and does it.
That makes sense.
It switches to this set value right here.
Okay.
And this right here, func3, is sent into this mux, and this mux has all the values for my ALU controller. And if I bring that up right here, these are the values for my ALU controller that I created. I've covered this in a previous video, but these are what each of the numbers mean. And all I'm doing really is translating this func3 value and this func7 value into the value needed right here at the end. Now what this stuff does down here, depending on the type, I may or may not have to do a different function. For example, if I'm jumping, I have to do a comparison. No, not a comparison. I have to do an addition. So that's what I do when I jump. And B type. What is B type again? I forget. Branching. Yes, for branching, you have to do a comparison. And depending on, so if I have a branch, then I will be doing a comparison.
Gotcha.
All right. What's
Alrighty.
next?
You said we're skipping the ALU. Yep. Let's go over branch log. Yeah, we can go into the mux.
Okay, because this is just in the data path. All right. Data path. RS1 goes into the A of our ALU, and RS2 or an immediate goes into the B of our ALU. And this is determined by this little value right here, which is our ALU SRC. And this is dependent on our opcode. All right, what's next?
Let's talk about branch logic. The branch logic part.
All right, this one's not too crazy. So what I do here is I take a comparison input, which is the 0 flag from our ALU. 0 flag is only high when the output of the ALU is 0. So by default, the output would be 0. Okay, and then function 3, if we look at for branch types, function 3 is determining which type of branch we're doing. And this PLA takes in the comparison, function 3, and the first bit of the 32-bit input, and this is taken straight out of the ALU. So if I go out of it real quick, this is taken from the output of the ALU, into our branch logic. The reason I do this is because when I do a comparison, like so, if the comparison is true, a 0 is output. If the comparison is false, a 1 is output, and just a 1. So depending on this one, function 3, and 0 flag, we get our result for whether we should branch or not. And the result for our branch goes into this AND right here. So the branch logic has to be true, and also the branch flag has to be set high in our signal control for a branch to happen.
Okay.
Right. What should we do next?
I think we can go scroll to the left a little bit and down. Okay, let's go to the last black box on the right. Just making sure we didn't miss anything. Yep.
Okay, this is the memory. I think I described this, I've overviewed this already, but I'll give another quick overview. So for our memory, we have an input address of 32 bits. We have a write data, so a data address of 32 bits. This comes from RS2. We have an access size, so how big of a size we're accessing. This comes from function 3. We have memory write en, so this determines whether we're writing or reading memory, and we have our clock. So we're going to go into it. Oh boy, this is a whole mess, but the address is 32 bits for 4 gigabytes of memory. And our data goes to each of these little sections. And each of these little sections takes an address of 24 bits. So 24 bits. Sorry, not 24, 26 bits, I believe. Yes, 26 bits. And we use 2 bits to select. Right here, we use 2 bits to select which one of these boxes we're taking our data from. And we use these 2 bits right here to determine what 2 boxes we're writing data to. Okay, let's go into one of these boxes. Take a look at it. So the first 2 is our byte select. So this selects what byte of memory we're addressing individually. So at 00, we'd go into this little decoder and it would come out and say, hey, we're only selecting this byte right here. And if this were 01, then we would select the next byte. And this is all dependent on the size of our data. Because if our data was a whole 32 bits, then we would select the whole row. Doesn't matter what this first value would be.
Gotcha.
This little select right here, this is selecting which one we're reading from, because we have each RAM is limited to 24 bit width maximum. So we can only have 24 addressable bits, so I have 16 of these RAM things. I'm just trying to get the full use of the 32-bit address. That's where that comes from, and this is, of course, our access size. All right.
So, do you want to go over the bottom half of where the data is shown, or do you want to show and explain where the data comes out of the memory register?
Let's do where it comes out of the memory register.
Okay.
Or out where it comes out of the memory. So this is our final mux right here. And all this mux does is determining what we send back to RD for our RD data in. So what we're writing to a register and where that signal comes from. So we can either write whatever comes straight out of our ALU, whatever comes out of our memory, or whatever comes from PC plus 4, program counter plus 4, which is right here. And this is only ever used when we're jumping. Because when we jump, we write program counter plus 4, which would be the regular next address, into our registers. And this signal is determined in our signal control. All right.
All right.
Let's upload some code and show it working.
Yeah.
So the way I
Do you have
upload,
any?
yeah, I have one preset. I have files preset ready to go.
Okay.
I'm just gonna walk through the explanation of how I get everything working. So the code I'm gonna start with is program A in the assignment. So this right here, I'm gonna copy it. And I'm gonna go to this website right here, Risc-V CPU Visualizer. And what this does is I can paste my code into here and assemble it, and it gives me the ones and zeros that I need to input into my ROM right here. The only issue is this ROM, if I want to edit the contents, it takes hex values, right? And I can translate it manually if I want to, but that's a hassle, and I don't want to do that. So what I did was I clicked download right here, and it downloaded the machine code as a text file. And I ran this through a custom Python script to convert it to this, just a bunch of hex values. And what I can do is in here, I can edit contents. Let's shrink this down a little bit. I can click open. And if I go to hex output 1, plain, and hit OK, bam. Now my hex values are stored in my ROM, and I can start running the code.
Nice.
So
Okay.
I'm going to go through each line at a time. I'm going to cite it. Hold on. Let me get this side on the other side. There we go. So this website also has a simulator where I can simulate the code working. So if it runs through the code, it shows me what is expected at each register. And this also shows me what's expected at each register. So what I'm going to do is I'm going to just run through each one at a time and explain what's happening. Just for the first program. I don't think I'm going to do it for all the other programs because there's a bunch. But I will show all the other programs running and the expected values. All right. You ready?
Yep. Let's go.
All right. So our first instruction is add I, x1, x0, and 10. Can you tell me what this is supposed to do?
So add immediate is supposed to take register. It's supposed to read register 0 and then the value 10 and write it into register 1, which will end up leaving register 1 equal to 10.
And why is that?
So from the way the project is designed is to read the input from our code, break it down, and to store it. And that is decided upon the structure that we did in the program. So if you could explain.
I was getting that x0 is always 0.
Oh yeah. Of course. Well, that was explained in the last program that
You're
we
right.
leave register 0 as 0 always. But yeah, you are correct. 0 will stay 0. It's empty, and then we're going to add 10 to it, which will leave it as 10.
Yeah, so we're adding 0 and 10 and storing that value in register 1.
Yep.
Correct? All right. I'm going to full screen this and we're going to go through it. So address 0 for our instruction memory. Bam. This is our instruction in ones and zeros, and then in decimal. So what happens first? Go to our signal. We're going to look, and we have an I type because we're doing add I. If we look at here, add I is an I type, correct? And when we have an I type, we are writing to our registers, and ALU SRC is high because we're using an immediate value. So we're using an immediate value. What's our immediate value? It's 10. Let's look at our immediate generator and show, hey, we have an I type. And we go here, and hey, that's 10. Would you look at that?
It works.
Now we're going to go into here. So we have 0 and 10, and then we have this 8. Well, -8 if it's signed, but if we go to here and we go to ALU control, 1000 is A plus B. So we're taking A,
Which is
we're taking B, our output should be 10. Awesome.
hey.
And then this goes into this mux, and because this value is 0, it goes all the way into our register. Now nothing happens in the register yet. We have the value of 10, right?
Mm-hmm.
Sorry, that's not right. That's RS2. Our value here is 10, the data in. So we have our value of 10. We have our register address of 1. We have our register write going to 1. Our register write, this is going to register 1. But nothing happens because we haven't clicked the clock yet, so nothing is updated. Oops. So when I go out and I manually tick the clock cycle high, we go back in. We see a 1, or we see 10 written to register 1. Awesome. But what also happens at the same time, when we click the clock cycle high, our program counter updates to PC plus 4, which is 4. 0 plus 4 is 4. And because this is updated, we're now working on our second instruction, which is
So would you like to go back?
This. Another add I. Add I x2, x0, 3. So what this should be doing, setting x2 equal to 3. Let's check our ALU. What's coming out of the ALU? We have 3. Who could have guessed?
I couldn't.
All right. Let's clock ticket another time. Let's check our register. Get register 2. We have a 3 stored in there. Awesome. All right. Our next would be an add x3, x1, x2. Can you explain what's going on here?
Yep, we're taking the information we just stored from the previous 2 instructions and adding them together, which would be 10 plus 3, which, as you can see, we get 13.
All right. So let's see. Here we have 10. Here we have 3. And our output is 13.
Yay!
And we are writing to our register. And what are we writing? We're writing 13. If we go down here, we can see what all of this means. This is our RD value, RD address. We're writing that to register 3, RS1, RS2, func3, func7. Cool. Am I good for another clock cycle?
Yep.
All right.
Let's go into subtract.
Oops. Now we're subtracting. I don't think this needs much explanation.
No, not really.
All right. So subtracting, we're subtracting 10 and 3. What do we get? Drum roll, 7. And we're storing 7 into what address? Address 4. Very cool. If we go in, address 4, it will be 7 once I click the clock cycle again. Let me click the clock cycle. Go into my register. Register 4 is now 7. Awesome. Okay,
Nice.
next and I. What does this one do?
All right. So this one, um, actually, you know what? You explain this one.
All right, and I. So what this is, x5 is our address we're storing the value. x1 is the address of the first value, and then 6 is our immediate. So we're taking 6 and whatever's stored in x1, and we're ANDing the two values together and storing the result in x5. So let's look at it going. So we have 10, rs1, 6 from our immediate, and when we AND them together, we get 2. Is that right? Yeah. 10 and 6 equal 2. If we go into here, we might be able to see it better. So an AND is when both bits are high. So the only time when both bits are high for A and B is on the second bit. So that's our output. Is 2. Pretty cool to see it working like that. And we are storing this value. Yes. We are writing it to what address? Address 5. So I'll click cycle again, go into address 5. Address 5 has a 2. Awesome. Next one. What's this one doing?
All right. So this one is doing a bitwise OR for 2 and the immediate value 8. And it's storing
Register
that
2.
in. So yeah, register 2 in the immediate value 8, and it's storing that in register 6.
All right. Let's take a look. We have 3 and 8. Let's look at our ALU. 3 and 8. Bam, bam, bam. What does that equal? 11.
Yep.
And it's going and it's storing that value. Taking it from here, going to here, storing it in address 6. Let's clock the cycle again. Next one is XOR.
XOR I.
Do you know what
It's doing
XOR
something.
does?
Sorry, yeah, exclusive, or it's
There you
exclusively
go.
one or the other. Sorry, and it's checking register 1 and the immediate value of 15.
So if we check,
Can you
we
explain how
should
that
have a 1
calculates?
here. That's 10. That's 15. Something's not right. It's not checking
It's not.
1, it's checking register 1. That's why.
Yeah, that's what I said. Register
Yeah,
1, and it
I'm
checks
confusing
the
myself
immediate
because
value.
10 is stored in register 1.
Yeah,
So when we
that's a
XOR
guy.
10 and 15, we get 5. Cool.
Yeah.
All right. That's storing it in address 7. Clock the cycle. Take a look at address 7. Address 7, we have a 5 stored. Awesome. All right, next one.
I think it's the last, right? Last
Yep.
code.
SLTI.
Yeah.
What does that do?
All right. So this is. I forgot the exact name. Is it store or is it shift? Because this one used weird wording. SLTI. Yeah, set less than immediate. All right.
So this is a comparison.
Yes. and it's using, what did it say?
Less than.
Yeah, it's comparing register 2 and the immediate value 4, and inside of register 2 we're holding the value 3, and it's saying is 3 less than 4, which it is, so it returns 1, which is high.
Yeah. And if we look, here we have 3, here we have 4, and our output is 1, because it is true. I think I might have got it backwards when I was describing the branch logic earlier. I couldn't necessarily remember, but
No, it's fine.
that's okay.
The document is scuffed.
Yeah.
It's all good.
And our 1 is being stored into register 8. Cool. And if we click our cycle again, our program counter goes to 32 and our instruction is empty, because that's all. That's it. That's everything.
Nice.
All right. Do you want to,
All right.
let's check our values in the registers.
Yep.
So let's look. This should, yeah, this has all of them in screen, just barely. Let's compare. X3 should be 13. X3, what is D? That's 13,
That is
right?
13 because
Yep.
A is 10, B is 11, C is 12, and D is 13. Yep.
All right. X4 is 7. That's right. X5 should be 2. That's right. X6 should be 11. That's right.
Yep.
X7 should be 5. That's right. And X8 should be 1. Yep. Awesome.
Yeah.
All right. Next is load and store. Loading and storing memory. In memory. I have the instruction already made for that, but before I load anything else, I'm going to keep my clock cycle high, reset my program counter, reset my registers, click the cycle again, and turn everything off. So this should be 0. Yep. I'm going to come over here, clear contents. Yes. Edit, open, and I've already pre-made this one as hex output 2. So we have 4 instructions. 1, 2, 3, 4 instructions. Yep. Okay. All right. Let's demonstrate the code again. You ready? I'm gonna skip through the first 2 instructions.
Yep.
So here we have instruction 0. Add I, add I, add I, add I. First 2, whoops. First 2 add I's right here should be done. Let me just move this one to the side like so. Now if we go into our register, we should have our 2 values. Yep, 0x20 and 99 right here. That's in hex. Cool. Now we're doing store word. So we are writing to our memory. We are using our mux here to add anything to our address if we have an offset, but we don't have an offset. And then this goes into our address, and we're storing 99. Cool. Tick the cycle. And in our memory, we have 99 in hex, stored in slot 32. Address 32. Great. Now if we tick it one more time, this should be outputting 99. It is outputting 99, and that is being stored into our register. Into RX12, we need to click the clock one more time. And it is now stored in register 12. So if we compare to here, register 10, or the memory of 0x20 is 99. We did just check that, and x12 should also be 99. It is. Awesome. So that's storing words and loading words. Storage and loading completed. We had a small issue with our memory storing stuff on rising edge instead of falling edge, and that kind of messed us up a bit, but fixed it, so no more issue. Yeah, we just reset it into here. And if we look into this, BEQ, branch of equal, always true if that is only high. And that is only high.
Yep.
So we are indeed branching. And if we go to C, branch is true. But what are we branching? We're branching from our immediate value of 4, moving that over to 16. Bam. Moving to slot 28.
Yep.
So we're going from 8 to 28. That's not right. Oh, shit. Fuck. This shift doesn't need to be here. You just... That's better. Yeah, it should be going from 8 to 16. Hey, there we go. Because we're skipping 12. We're skipping
Yeah.
one line,
Yeah.
one address
Well,
line. So that is skipped.
yeah.
And our next address would be this, which would be
All right.
16. All right. Tick the clock cycle. So this is not executed. So we're not putting 111 into register 3. We're putting 222 into register 3. Right?
Yep.
Okay. So now if we go look, 222, whoops, 222 is going into here at register 3. Awesome. Clock tick again. What are we at? What does this do?
Checks if 1 and 2 are not equal. And that's not true because they are the exact same, so we do not take that branch.
Okay. And if we look, we have a 0 flag going into branch logic, but branch logic is not outputting a high, so we aren't branching. And instead of branching to where L2 would be, instead we are just jumping to the next address. Awesome.
On to the next instruction.
Next instruction, setting register 4 to 7.
Mm-hmm.
All right. Let's see. Here we have 7. 7 is going into register 4. Awesome. Clock cycle. Next we have jowl. What does this do?
It does two things. So we're going to store this return address into X5. We're also going to jump to the next set of instructions, L3. So we're going to skip the next line.
So what's up with X5? What does that mean?
So the next set of instructions, which is add immediate X6 and then register 0. Well, we're going to take what's in L3 and we're going to put that inside of register 5.
Close but no cigar.
So
What actually happens is X5 is storing what the next instruction would be instead. So instead of storing L3, it's storing the program counter plus 4. If we look at this right here,
right,
the little card,
I got it mixed up.
yeah, we go to jump and link, which is what we're doing. We look over here, we're doing return our storage register. It's PC plus 4, and we are jumping to program counter plus immediate. All right. So let's execute it. Jump is high. Instead of going to 32, we're going to 36. So our next instruction is 36. And in our, because 32 would be the one, if we weren't jumping, that's our value here. And we're storing that into register 5. Click. Finally, we have final command, which is this.
Yep. Which is just store the value 10 inside of 6.
Yep. And if we look, we're storing 10 to register 6. If we look into our registers, compare our values. X3 should be 2222. X3, DE. What is DE in binary and decimal?
Oof.
Watch this. Hey Siri, what is DE in hexadecimal to decimal? It's thinking. DE in hexadecimal is 222 in decimal. There you go.
Okay.
All right.
That was like
X,
16 to something plus. It's
X4
weird.
is 7. X6 is indeed 10. And X5 contains the address of the instruction after the Joe. And X5 does contain 32, which is 020 in hex. Awesome. Any questions? Is there anything else left to cover?
I think we covered everything.
All right. Well, thanks for watching. I know it's been a long video, but big project. And you got to cover every little bit of it. So, yeah. Here's the full thing in one frame. There we go. Awesome. See you next time.
Yeah.